In the talk, we will introduce our CVPR work FINR, flexible spectral bias tuning in implicit neural representation by variable periodic activation functions. The contents include 4 parts. The performance of INR is limited by 2 aspects, the spectral bias and the limited frequency tuning. From the first aspect, existing INR techniques suffer from the well-known spectral bias, meaning that INR tends to learn low-frequency information and struggles with representing high-frequency content. As shown in the top left figure, the fitted results are overly smoothed. Existing solutions often focus on encoding high-frequency content in the input or activation functions. However, the expressive power of INR is restricted to functions that can be represented using a linear combination of certain harmonics of the pre-encoded frequencies. This restriction results in imperfect performance when there is a mismatch between the predefined frequency set and the characteristics of the signal itself. The function set that Siren can represent can be enlarged by increasing the initialization range of network parameters. However, since the sine function is non-convex, careful initialization is required to keep the inputs within -pi. Otherwise, Siren will not converge well and will lack accuracy in representing signals. As shown in the left figure, there is a performance gap between theory and practice. To overcome the capacity convergence gap, we propose FINR, which introduces a variable periodic activation function, as shown in the right figure. Compared to Siren, FINR can more effectively utilize the activation function's definition domain by initializing the bias vector to different ranges. This allows different subfunctions with varying frequencies within the definition domain to be selected for activation. To address the limited frequency set of traditional initialization methods, we propose a novel scheme that initializes bias using a uniform distribution over a larger range, allowing for flexible tuning of the supported frequency set. From the geometrical perspective, the supported frequency set of FINR increases with the increase of the initialization range of bias, and the supported frequency set of Siren is a subset of that of FINR. From the neural tangent kernel perspective, increasing the bias enhances the diagonal elements while keeping the non-diagonal elements very small, resulting in a diagonally enhanced kernel. This stronger diagonal property improves shift invariance, reducing coupling between training set coordinates and facilitating better signal learning, as shown in the left figure. In subfigure D of the right figure, a larger initialization range for the bias significantly increases the number of larger eigenvalues. Consequently, FINR excels in learning high-frequency components. Based on the above analysis, the supported frequency set of FINR increases with the initialization range of the bias, providing more high-frequency details from the third column to the last one. Additionally, as analyzed from a geometrical perspective, the supported frequency set of Siren is a subset of that of FINR. Therefore, FINR offers clearer details than Siren under the same initializations, as seen in the second column versus the third column in the figure. We compare FINR with 4 classical INRs, Fourier feature embedding, PEMLP, INR with periodic activation functions, Siren, Gaussian activation functions, YAUS, and wavelet activation functions, wire. For image fitting, FINR provides clearer results, as demonstrated by the text 67-foot and SBS in the cyan and green boxes, respectively. For 3D shape representation, we zoomed in on 2 representative regions, the low-frequency smooth pectoral and the high-frequency rough shank. Compared to these baselines, FINR consistently performs well in reconstructing both low and high-frequency components. For neural radiance fields optimization, the figure highlights FINR's advantage in representing high-frequency components. The holes, red boxes, and highlights, green boxes, in the truck frame are over-smoothed by all baselines, while only FINR provides clear details. Thank you for your attention.